we are going to start talking about an official form of solving the linear programming problems. And we will get to learn a technique which would allow us to solve problems. This is called the Simplex Method. And to start discussion on Simplex Method, we need to make a little bit of why these things work out. And you will probably help me as we are going through these things. Couple of trivial questions. One, if I give you an option between these two, and I'm telling you to maximize these values for me, and I'm telling you that x1 and x2 right now is 0. Right now it is 0. But I want to increase them, and I can increase them as much as I want. But I can increase them one at a time and give you an option. How many of you will choose x1 to increase, and how many of you will choose x2 to increase, and how many of you will choose not to increase any one of them, and how many of you will choose to increase all of them? First, how many of you choose not to increase them at all? Raise your hand. How many of you would choose to increase both of them at the same time? No hand. How many of you choose to increase x2? Okay. You're going to increase, that's 3 of you. You're going to increase x2. How many of you choose to increase x1? The rest of you. Okay. How many of you care not to answer to any of those questions? Because several of you didn't raise your hand in either cases. In any one of those cases, give. Okay. The ones that wanted to increase x1, do they have one person to explain why they wanted to do that?
Well, for me, for x1, the coefficient of x1 is larger than the coefficient of x2, so it will reach infinity quicker.
And for you that wanted to increase x2, 3 of you, 1 of you? Looks better today?
Yeah.
Yeah. I felt internal connection to x2 today. Yeah, welcome. Okay, so basically, if you're given the chance to increase one of them at a time, then the choice seems to be x1 because it has higher rewards. We're trying to maximize. If I increase x1 by 1 unit, I get $5 back. And if I increase x2 by 1 unit, I get only $3 back. So it makes sense. Whenever we put max or min, we are talking about objective function. So if I'm given a chance to increase a variable, I'm going to go with the one that has higher coefficient. Where? In objective function. Now, if I told you that there's a condition also that x1 plus x2 has to be equal 10. What would happen to that selection? Because last time I would say I would increase x1. How far? As much as you can. So nothing is stopping me. But if I have a constraint, constraints are like barriers, stopping you from doing something. It is telling you that you can't go wherever you want. There is a restriction. So if I say, okay, how far can I increase x1? You would say up to 10 units. Not more than that. So what is the answer to that? Is 50. Because it would go as far as you can while still satisfying this requirement. If I had less than or equal, still the same thing. What if I had greater than or equal 10? That answer will be infinity. Because I can increase it as much as I can, and this is telling me that it has to be greater than 10. So I can increase it up to infinity. Okay. Now, let's keep it the same way. That with less than or equal. So the maximum that I can go is 10. Let me write another one too. And I say 2x1 plus 3x2 less than or equal 8. And I ask the same question again. Same question again. Which one should I choose? x1, because it looks like having a better reward, because that coefficient is larger. When you come here, this is telling you that you can increase x1 up to 10 units. So you say, so far so good. I can raise x1 to 10 units. But if I raise x1 to 10 units, something is going to go wrong in here. 2 times 10 is 20. You bring it the other side, becomes negative 20. That becomes negative 12. You would run into trouble with the other variables. So this is telling you something else. This is telling you that you can raise it up to 10. How much can you raise it using this one? What is the maximum that you can raise it without causing trouble with the other variables? Probably 4. Probably 4. Why 4?
That satisfies both conditions.
Because the other side of it is 8. The maximum that you can raise this without putting other variables into negative range is 4. Where did I get 4? Where did I get 10? If I have another one which says 5x1 plus x2 less than or equal 10, how much can I raise x1? 2. Where did I get 2? Right-hand side over that coefficient. So the idea is pretty much make sure that you're looking at the right-hand side and you're looking at the coefficients.
Can we do one that's greater than us?
Can we do, let's change this to 13. Which one is going to be selected if I want to raise it? x2, because it has larger coefficient. These are just common sense stuff. We start from the common sense and we go a little bit further. So x2 is natural selection. You look at 5 and 13 and you say x2 has a better reward. And I'm trying to maximize, so let's go with the x2. So I come down and I say, well, if this were the only thing that I had, I would go infinity with x2. But then I look in here and I say x2, 10 over 1, the maximum that I can raise x2 is 10. I come down here, 8 over 3, the maximum that I can raise x2 is 8 over 3, because 8 over 3 is smaller than 10 over 1. And then I will look in here, another 10 over 1. So between 10 over 1, 8 over 3, and 10 over 1, the one that I can select is this one. So I can raise x2 up to 8 over 3. Why did I choose 8 over 3? It will satisfy all 3 constraints. If I chose 10, it wouldn't satisfy this. So I go with the minimum on the constraints. I go with the maximum on objective function, but I go with the minimum on the constraints. So the first decision that I have to make is find out one variable that I want to increase, and then look at the constraints to find what is stopping me from increasing it as much as I can. And in this case, this constraint is critical. It is telling me this is as far as you can go. You go any further, you will create problem for the other variables in the constraint. What is that type of problem that we are talking about? It will make the other variables negative. Remember that there is always a non-negativity set of constraints as we are talking about LPs. So in this case, the approach, the common sense approach, is pretty much like this. Now, let's take it a little bit further. Let's take it a little bit further and add a couple more in there, variables. Okay. Well, first, let's put x1, x2 greater than or equal to 0 in here, such that we are sure that we are talking about those conditions. Now let me add another set of variables in here. I would add 2x1. Okay, this is better. I would add 2x1 minus 7x2 less than or equal 20. And then you would say, what is the impact of this? I'm trying to increase x2. I'm trying to increase x2. What is the impact on this constraint? If I increase x2, would it make a problem for the other variables? And when I say about a problem, what is that I'm talking about? Making them negative. If I increase x2, would it make a problem? No, because the higher the x2 variable value, this thing become negative, will come to the other side, become positive. So that variable or any other variable in that row to adjust has to become even more positive, which is okay. It will not be negative. But in this case, if I increase that to 20, this becomes 60, will come to the other side, becomes negative. Those variables had to become negative to adjust to this. And that is the problem. Yes.
I'm not understanding that last part, the explanation for this last constraint.
Okay. Let's say that this was equal instead of less than or equal. And this was equal. So I can increase x2 as much as I can. It will get to 8/3. This becomes 8. Will come to the other side, it becomes 8 minus 8. Will be 0. So what would x1 do? Becomes 0 to adjust the equation. As you increase that one, this keeps going down until it hits 0. Now let's make that 10. This becomes 3 times 10, 30. Comes to the other side, becomes 8 minus 30, becomes negative 22. What would x1 have to be? Negative 11, which would violate these conditions. That's a problem. The problem that we are talking about is called the infeasibility. This will make the problem infeasible. So that is, these are just outside. This is a common sense we are talking about. So when I have a negative coefficient, it's really no problem at all. It's only when the coefficients are positive that I may have a problem. Okay? And how do I locate the problem constraint? by finding that ratio. 10 over 1, 8 over 3, 10 over 1. And this I don't do it at all because this is not a problem. Let's do another one. Let's say that I have 3x1 less than or equal 15, or less than or equal 17. And I'm trying to raise x2. What is the coefficient of x2 in this one? 0. There is no x2 in here. That's a 0x2. There is no x2 here. So if I'm trying to raise x2, there's a positive x2 here, there's a positive x2 here, there's a positive x2 here. They all might create the problem if I raise them too much. There's a negative x2 will have no impact on me raising that value. And what about this one? There's no problem here either. There's no x2 at all in here. So when I look at this, I would say I'm going to find that critical ratio. And I'm going to find the minimum of that critical ratio. That make sense? I'm going to, when I want to increase that, after I have made my decision that I'm going to increase x2. So the first decision that is going to happen is I would identify what is that I'm increasing, and then I would say, let me look to see how much I can increase it. And that how much is found by finding a critical ratio. 10 over 1, 8 over 3, 10 over 1. This is negative, no problem. This is 0, no problem. So among those three, I'm going to find a critical ratio, and I will choose the minimum of those critical ratios. And in that case, it would be this one. Now that we have talked a little bit about the common sense stuff, let's put these understandings, its basic understandings, into mathematical terms and see how the solution strategy is. Let's say that I have a problem, max z equal 4x1 plus 3x2 plus 5x3 plus 2x4. Subject to 5x1 plus 2x2 plus 3x3 plus 6x4 less than or equal, and 3x1 plus 4x2 plus x3, put that minus x4 less than or equal 24. With x1, x2, x3, and x4 greater than or equal to 0. Please pay attention as we are going to bring all the concepts that we have learned so far and connect them with each other to talk about the solution of this little problem. First is that we should write them into standard form. So we are introducing the standard form of the problem by saying plus S1 and plus S2. Okay. So I'm going to add S1 and S2 in here also. Must do that. If I don't do that, what does it mean? Means S1 and S2 are unrestricted, which means they can be both negative and positive. All these discussions will go out of the door. It is that important to put these conditions down there. And says, oh, like to say, you know that. No, I don't know that. If you don't put it in there, yes, I know that. You meant it was unrestricted. Okay. So this must be here. Again, the other thing is that when we convert a problem into a standard form, we have to do that on the Z also. I'll hold off on that one for a second and then come back to that. The other thing, now we are tapping back into what we have already learned. You look at this and you say, two constraints, two equations, 1, 2, 3, 4, 5, 6 variables. Two equations, 6 variables. Two equations, 6 variables. And then you say, the only way that I can solve this and find a solution is if I convert this problem into a 2 by 2, 2 variable, 2 constraints. Because I can solve a system of 2 unknown, 2 equations. That's what I have to do, because there are 2 equations. I can solve a linear system of equations if there are the same number of variables. Then you would say, okay, there are 6 variables in here. So 6 minus 2, there are 4 variables, too many. 4 variables, too many. Let's get rid of 4 of those variables. Which means you're going to assign values to 4 variables. So we can select out of these 6 variables, we can select. For example, we can say x1, x2, s1, s2. And we can assign them values. Can I assign these values? 9, 3, 7, minus 8?
No.
Arbitrary means I can do anything that I want. Would that make sense? No. Why not?
What about the non-negativity?
Because there are some things in here which says, didn't you see that? And I say, so what? You say, you assigned the minus 8. Can't be negative. So let's change that to 8. Can I do that? I can. Anything is stopping me? Not really from that concept. And if I plug these values in here, if I plug those values in here, just by x1, forget about the rest of them, just by x1, 9, 5 times, that's 45. The other side, 30. To compensate something in here has to become negative. Regardless of anything else, the others are also positive values. Something in here needs to give up. We said x2 is 3, so that is a positive value. We said s1 is 7. So these others have to somehow adjust to what needs to be done. And we say, what is the difference between this one and this one?
That can satisfy everything.
That's also another set. 4 variables are assigned values. What is the difference between these two? There is a name that we used. The answers that are going to be gotten from here could be feasible, could be infeasible. In this case, you can easily see that it is infeasible. Could be feasible, could be infeasible. The answers that you might get from here is the same thing. It could be feasible, it could be infeasible. But there is a difference between these two. When your arbitrary variables are assigned the value of 0, what do you call that solution? We use the terminologies of basic and non-basic. When the arbitrary variable values are assigned the values of 0, you're talking about basic and non-basic variables. In this case, this could be anywhere. When they are basic and non-basic variables, where are these solutions? On extreme points. They are on the extreme points. When you have this, the solutions are on the extreme points. The optimal solution of any LP is at an extreme point. So it doesn't make sense to assign values like this, because there is no guarantee that they are on the extreme point. In fact, there is a guarantee that they are not on an extreme point. But when you assign them like this, there is a guarantee that they are on an extreme point. But remember my first sentence. The first sentence was, I don't know whether this is a feasible solution or not. When I plug it in, I will find out. I don't know whether this is a feasible solution or not. And then you say, yes, but you said it is on an extreme point. Yes, but extreme points can also be infeasible. It is significant. It is on an extreme point. But is there a guarantee that they are feasible? we are also recalling one thing, and that was the concept of adjacency. We talked about adjacent extreme points. And we said there is a difference between two adjacent extreme points. Who remembers what that difference was? So on adjacent extreme points, so I say, well, if I have an extreme point, I can move toward these optimal solution by just using the adjacent extreme point. If this is one extreme point, are these basic variable or non-basic variable? They are non-basic. Whenever your arbitrary values are assigned the values of 0, they become non-basic variable. So what are the basic variables in here?
X3, X4.
How do I find x3 and x4? Plug the values in here, and I would end up with a 2 by 2 linear system of equations. For that, it would be x3 and x4, so it would be 3x3 plus 6x4 equals 30, and x3 minus x4 equals 24. Now, although these values are 0 and they are okay with that condition, these values I have to calculate. And if they end up to be negative, then it is infeasible extreme point. If they end up to be positive, then they are feasible extreme points. And if I have a feasible extreme point, I can go to the next feasible extreme point. From that, I can go to an adjacent feasible extreme point. From there, I can go to an adjacent feasible extreme point until I hit the optimal solution. That concept is gone. Now, but in this way of just assigning variables and so on, what should I select to make sure that it is the right selection? In this case, this is how I approach it, and we will talk about this a little bit more next time. This is how I approach it. I would say I will find one variable in here that only exists in one row only, not in any other rows. And its coefficient is +1. And I do that for every row, different variables. So I will look in here and I say, oh, there is an S1 in here that is not here, it's not there. Its coefficient is +1. And in here, and you say, oh, I have an S2 here with a coefficient of +1. See? Well, those are my basic variables. They are nowhere else. So I'm going to assign everything else 0 and keep those. S1 equals, when I solve it, x1, x2, x3, and x4 are assigned the values of 0, and I would solve the system. S1 becomes 30, and S2 becomes 24. What would the Z be? There's no S1, S2 in Z, so Z will be 0. I say, oh, that's easy. That is easy. So now I have a point, an extreme point. I have an extreme point that is feasible. Zeros and positive values. So I have an extreme point that is feasible. So I start from a feasible extreme point, go to an adjacent point, go to an adjacent point until I find the optimal solution. We will continue with this. My recommendation is take a look at these things. Take a look at your textbook. Take a look at these things. We continue next.